So good morning, good afternoon, good evening. Thank you all you that are connected today to attend a new exciting talk in the series of IEEE Sequence and System Society Rio Grande do Sul Talks 2021. So today we have the pleasure here to have Professor Malgorzata Chrzanowska-Jeske from Portland State University. And the chair of this session today will be Professor Maciek Gorzalek from Krakow in Poland and former president of IEEE Sequence and System Society. So now the floor is with you, Maciek.
Thank you, Ricardo. It's a pleasure to be with you here today, and I have to thank Ricardo for organizing this very exciting series of talks. I think it's a very unusual opportunity that was found during the COVID period, where all of us we stay at home, but still we keep in touch thanks to this kind of special events. And actually, it's amazing that we can meet people from all over the world at this kind of events. It's a special pleasure for me to introduce today's speaker, Malgorzata Chrzanowska-Jeske, who is of Polish origin, but for many years she is living in the US and currently working at Portland State University. And well, you can read the details of her very wonderful achievements in the announcement. I will only stress that Malgorzata is one of the leaders in the research in three-dimensional integrated systems. So her laboratory is one of the leading laboratories in this domain in the world, and she has fantastic achievements. And you can see, and we are very proud to have her presenting her latest thoughts and results at this meeting. I think it's time to start the talk. So without further ado, I will give the floor to Malgorzata to bring to us this presentation entitled Heterogeneous Integration, 3D Systems and Emerging Devices. I think especially the emerging devices for me, as I'm working a little bit in this domain, I'm really interested in seeing and listening to this presentation. So Malgorzata, the floor is yours.
Thank you very much, Maciek. Thank you very much for your very kind introduction. And I wanted to say thank you to Ricardo for inviting me to give a talk in this series of talks, which has been going for months now, and a really a great addition to our to the program of presentation in series, especially during those times of pandemic. As Maciek said, I work right now at the University in Portland, Oregon. So just the first few slides to actually show you where my university is. However, at this time, I'm actually in Warsaw, Poland, and I actually can hear that there is a thunderstorm coming. So hopefully it will not disturb too much this presentation. Here are a couple of pictures from Oregon. We have beautiful mountains and the Pacific Ocean and beautiful lakes. And there's a lot of people doing outside sports in Oregon. A few more slides from Portland, from the city where I work, and you can see the gorgeous mountains of Mount Hood, which is quite close to Portland, and where a lot of people go for skiing in winter. And here is a few views from my university, which is located in the middle of the city, and the campus is in the middle of the city. And we are hoping that finally we'll be able to go and do our lectures in person. However, the situation in Oregon since I left a few weeks ago actually changed for the worse from the point of view of the pandemic. So we'll just see. Okay, so let's talk about the heterogeneous integration, and this is really something which fascinates me. A few years ago there were things which were unimaginable, and now it looks like that they are possible, and even more will be possible. So what is 3D integration? And this is just kind of recapturing everything, because I'm pretty sure that many of you, probably most of you, are quite familiar with that. So we can talk about the 3D wafer level packaging, when we'll put the separately fabricated chips all together in different arrangements, and the connection between those wafers are done through the external wires. So that's one type. And the second one, we are looking at interposer 2.5 or 3D interposers, where the interposer is a separate chip which just contains the connections. And then we put the separately fabricated chips on the top of interposer and using it for the connections. Then the next step is 3D stacking integrated circuits, where are individually fabricated chips, specially designed to be stacked vertically, but they are communicating not through the external wires, but they are communicating through what we call through silicon vias, which are vias in the silicon in between different chips. And the fourth one, probably the most latest one, is our monolithic 3D ICs, where we have multiple layers of active devices fabricated one on the top of the other. And generally speaking, we'll have most of the wires on the top of the latest of the top level of active devices. So what's heterogeneous 3D integration? So we can say that those are separately manufactured components which are assembled into the higher level system in order to improve functionality and characteristics. And what are those components? The components actually, any individual dies, could be CMOS processors, memories, MEMS devices, passive components, different substrate materials, and they are all assembled into one integrated system, into one package. And as you can see, this could be different technology, gallium arsenide, silicon, carbon nanotubes. In the future, we're thinking about being able to fabricating chips with the biosensors, chemical sensors, nano devices, and stacking them all together. Oops, sorry, did go too far. Okay. Oh, I'm sorry, I think that I'm trying to make it expected to go faster and it goes slow. Just a minute. Okay, so here it just some view on the journey from the chip integrated system when we had 4 bipolar transistors to what we have right now. So we moved from a few bipolar transistor to then PMOS transistor integrated together, NMOS, CMOS, and then 2013 you can see 2.6 billions of FinFET stuck together. 8.5 billion transistor in the Apple chip. And then just recently, 2021, Cerebras with the wafer scale engine, which has 2.6 trillion transistors. And as you can see, this is done with TSMC 7 nanometer process and have 850,000 cores, and it's done on 12 inches wafers. And actually, you can buy one for $5 million US, or you can get it if you're a supercomputing center. Not really getting, but you probably still need to pay. But looks really really interesting. So this actually started when we had packaged individual chips on the PC board, and then the connections between those chips were too long. We're trying to move them closer together. So this is how we developed ideas about System-on-Chip, when we wanted to bring different types of chips on the one common substrate and fabricate them during the same technology process. And it's actually turned out to be quite challenging to do it for different technologies. It was low yield, there was huge fabrication costs, testing, and so on. So System-on-the-Chip was mostly successful for different digital application. It turned out that if we tried, when we tried to integrate technologies here, like analog, digital, and others, then the costs were going astronomically high up with each technology added. So it was really very expensive, not that practical. So those design challenges, which we've seen in 2D integrated circuit, had to be solved in some other way. So big issue was the limitation by the amount of interconnect which we needed to have, especially with the scaling of the devices, which were getting smaller. We're able to put more of them on the chip, and therefore there was the increase in the length of interconnects. And even with the new technologies allowing us to put many metal layers on the top, those connections were getting really, really long. So this ideas of digital MEMS, RF, analog on one chip was not really satisfying. And then the idea of stacking the chips one on the top of the other with the internal connections came through. Looking at the main components of integrated circuits, those are devices, transistors, and of course interconnects. So as you can see with those pictures here, which shows the 0.35 micrometer technology going from that to 40 nanometer process, you can see that devices are getting smaller and smaller, and the larger part of the chip is actually occupied by interconnects. And because of the higher density of devices, the number of connections and the length of wires are going up. So influence of interconnects are really, really very important and have to be taken very seriously into account. There's of course power. So the big two issues, the delay and power. And with the power, with smaller and smaller devices and voltage going down, there's increase in the leakage power, and power, dynamic power, which is related to the frequency, is also the big problem. But in addition to the power dissipated in modules and blocks, there's of course power in connections, and that depends very much on the length of interconnects, on the number of buffers, and as you will see later on the VS. So this is the challenge which needs to be addressed, and the challenge was not really addressed by System-on-Chip or System-in-Package or System-on-Package, but it was much better addressed in 3D. So I just show the slides, which basically shows that with all the scaling, we see that the power, because of that, is going up, and this is due to power in wires and power in buffers. So looking at the interconnect power, which depends on the length of the wire, cross-section, resistance, capacitance, which of course depends on the temperature. This is number of vias, number of buffers. Those long wires, it's really the big problem and introduces high power. So bringing blocks together, smaller chips stacked vertically, and connecting through TSVs with multiple transistor levels makes actually sense. So 3 integration is something which will allow us to solve some of our problems. Unfortunately, will introduce the other ones. So let's first look at the system, which is 3D IC stacking. And it started, as I mentioned before, with those system in package and on package, and limitation which was introduced by Systemonchip were addressed by the system on package, and then we were able to fabricate passive devices and other microwave devices in the substrate, and this allowed the system of package to overcome the limitation of the previous solutions. So this is how you can represent the evolution of packages, and then at the end we see those three-dimensional integrated circuits. This is just the summary of the evolution of 3D, coming from the bottom, from the 3D package to the monolithic 3D integration. So let's look a little bit more on those stacked 3Ds with through silicon vias, and really the through silicon vias are the big important challenge for those chips. You have the systems which are composed of independently fabricated integrated circuit. However, they are independently fabricated, but they have to be designed that in the coordinated way. There are issues with wafer aligning, thinning, bonding, and all this needs to be technologically sound. But all this is connected using through silicon vias, and those through silicon vias unfortunately introduce some problems, and some of them are thermomechanical stresses, which influence performance of the neighboring devices. What we also can see that with the big stack of different chips with the different density of devices, there will be the problem with heat distribution, and depending where we will have the heat sink, the temperature on different layers will be different. So this is just the example of one of the first 3D IC. One is the memory cube, the other one is the FPGA, which were developed, one of the first ones. But what I really want to talk about a little bit more, this is about TSV technology, especially that we are focusing a lot on physical design of those new systems, and TSVs are really the big part of how those systems have to be designed. So what you see here is just the simple view of through silicon via with the which connects some metal layers at the bottom tier to some metal layers on the top tier, and it has the liner and the barrier just to make sure that the whatever is the material used for TSV is not leaking into the surrounding area. There are different types of stacking those dies. The most common is face to back, and as you can see that there is a bottom chip, which at the bottom is their devices, and then their level of interconnects, and then on the top we see the similar chip with the devices at the bottom and interconnects on the top, and there is a via which connects them. There are two other possibilities when you can do it face to face or back to face, but those are not really commonly used. There could be different ways of how to stack those systems together. It could be wafer to wafer, die to die, or die to wafer, and which one is chosen depends on many many parameters. However, probably due to the yield concern, the most typical is die-to-die. And also on the bottom drawings, you see the different kind of vias, which are called via first, via middle, via last, and it depends when the via is fabricated in the process of fabricating devices and interconnects. The most popular, at least most popular for signal vias is via middle, which connects the top layer of the metals on the bottom device layer to the bottom metal layers on the next device layer. So I mentioned those thermomechanical stresses, which are caused by through-silicon via, because I need to mention that the sizes of through-silicon vias are quite large. And later on, we'll see the picture in comparison. But because of the sizes of those through-silicon vias and different thermal coefficients of thermal expansion between materials of here is just the example of copper, which would be used as a filling material for TSV, and the silicon surrounding that. So because of that, there will be different stresses and could cause failure with devices or with interconnects. So on the left side, you see the nice picture of the drawing of the cross section without any stresses, and then on the top you see the stress caused by the surrounding vias on the transistor, on source and drain of the transistor and some other area. And this kind of stress can cause changes in the mobilities of the electrons and holes, actually most of the holes. It can only cause the change in the threshold voltage for those transistors. And on the bottom, you see the squeeze, which can cause problems with interconnects. So there's simulations which are done in order to see the influence of that. And what you see here, this is the simulation looking at the changes in the mobility of electrons and holes in the certain distance from the VI. VI is in the middle, and if you see the red color, it means that there are bigger changes in the mobilities. So in order, and then on the right, two pictures on the right, you see the influence of the via on the threshold voltage of the surrounding devices. So one of the reasonable solution was to actually define some safe area around those vias, to call them keep out zone, and do not place the devices. So in the area where the changes could be significant, there will be no device placed. The consequence of that, of course, is that the area which is needed to be reserved for the via, which is quite large, is increased by additional area needed for KOE zones. Actually here you can see the landing pad for TSV plus surrounding keep out zone, and keep out zone will be different for different vias done with different materials, different sizes, different aspect ratio, and so on. When placing TSVs on the chip, they could be placed as individual TSVs, or they could be placed what is called on the islands, as something which you see on the top of the picture. And then again, how the stress will be distributed depends on the ratio between pitch between vias and their diameters. And again, when we have the TSVs arranged in the islands, then we need to recalculate what should be the keep out zone reserve in order to make sure that devices are not influenced. So this is just some pictures showing that those TSVs could be done with mostly with the most typical would be copper, but it could be also with tungsten, or it could be with carbon nanotubes, copper with carbon nanotubes, and so on. Each of them have a little bit different resistances and different parameters. There will be also different sizes and different, actually even different shapes. So another issue, which we'll talk a little bit later, is when we calculate, trying to predict what would be the delay in the chip which we are designing, then we have to carefully consider TSVs and also TSVs capacitance, which could influence the delay of the nets. And what you see here is showing that it's important to decide very early on the position of TSVs, as TSVs will influence the length of the interconnects, which you can see on the pictures on the top, depending on the location, and of course location and which nets are assigned to specific TSVs. And once we know that, then we can do the better prediction of how many buffers we'll need once we know parameters of TSVs. And there are different methods how those buffers can be estimated. And it turns out that it's actually quite important to estimate the number of buffers, because they influence not only delay, but also influence power quite significantly. The way when we decide location of TSVs is also important. Are they individual? Are they in the islands? Are we just do the placement of the blocks and see where there are white spaces and try to introduce TSVs there? Or do we actually try to do it in more integrated way? So looking at the process of designing those systems, there's a lot of challenges, and probably I will talk a little bit more about the physical design, specifically about the floor planning, because this is what we are working on. But of course, there are other issues with testing thermal interconnects and so on. So importance of physical design of through-silicon via and actually designing them very early is, I already made some arguments that this is very important, as we are looking at the horizontal block location, their wire length, distribution of TSVs. There will be vertical block location, and the alignment between different block location could be overlapping separation. And of course, the arrangement with the TSVs, are they islands or individual location? What are they, K or Z, and everything? And the best way to do it and decide it is during the floor planning, and the floor planning needs to be done as early as possible, so the prediction of and the best possible estimation of how the system will work will be done early. So performance and power of 3D ICs with TSVs are really decided during the 3D floor planning. So just one slide about what the floor planning is for those who are not really working with that we have at the input, we have the information about what's the number of modules, what's the areas of those modules, what's the connectivity, what are the constraints in terms of their geometrical placement, and any other constraints which are needed. And at the output, we're generating the position of the modules. At the same time, for example, optimizing area and wire length. Area and wire length is the very typical, but it's just only the beginning of the parameters which we have to optimize. So this is how it would look for 2D. And when we move from 2D to 3D, and on the picture on the right, you see just two layers, which shows that actually there are blocks which needs to be aligned. And this needs to be during floor planning, and I will talk a little bit later about it, how we are, can we do the floor planning separately for separate layers, or we need to do it all together, or is it enough to use some vertical constraints in the floor planning, separate floor planning of different layers? On the bottom picture, you see actually the floor plan of the system, which has 4 layers stuck together, and some of the modules had to be aligned vertically. So you can see that sometimes that alignment actually could be challenging, and that could enlarge the size of the chip. So so looking at the floor planning for 3D, this actually becomes more complex because of TSVs, which we need to include. They are large, they need space, and we need to have that space reserved for them. So we need to make the choices also. Do we want to do individual TSVs will be arranged in islands, the same size islands, how this needs to be done. And then, depending on that, of course, the complexity of your algorithms is increasing, but also the quality of the final solution will be changed. So with the in my group, we've been working on placing modules and optimizing position of modules together with through silicon vias. We started with islands, and with the islands which were of the same sizes. It was, and we were doing dynamic assignment of nets to TSVs. But then we realized that's really what it needs to be done. It should be dynamic TSV island sizing. So we could actually use the opportunity of much better optimizing the performance when the sizes of islands are different. And with that, it came the need of looking at modeling very carefully vias, and especially vias capacitances. There are 2 most important components of capacitance of the via, and we're looking at the via middle. The one is the coupling capacitance between 2 TSVs, and the other one is coupling capacitance between TSVs and top and the bottom neighboring wires. And calculating and predicting those coupling capacitances are becoming quite interesting and challenging, especially when we think about that the distribution of wires could actually be different on the top and the bottom, and also the sizes of the wires could be different. Especially in predicting the behavior, predicting delays of TSVs, it would be really almost impossible to calculate capacitance of each of the vias. So we're using the values for the largest possible capacitances of the via, and depending on the sizes of the islands, such via location could be identified. And this is what you see on the top picture, but then on the bottom, it actually shows that it is possible that some of the islands which are completely separate, they can come close together, and then this also needs to be incorporated into the arrangement. So kind of gets quite complicated. So everything, all those dependency comes into optimizing the geometrical location of blocks and TSVs, which sounds kind of trivial because those are just blocks and some blocks of TSV, but behind that are actually quite important optimization which needs to be done, and the influence of that arrangement is very strong. So a couple of things which I want to show you which needs to be considered is that when looking at the distribution of nets, and what you see here on the left top, this is for when the chip is designed for in 2D arrangement, and this is for IBM benchmarks with 200 modules. Then when you look at the total 3D, the total length of the wires is shorter, and those color graphs are for the distribution of nets on the different device layers, and this is the chip which has 4 device layers. And on the right, you see just you see again the distribution of those nets, and on each layer separately. So as you can see, layer 2 and layer 3, those in the middle, they will have the most of the interconnects, and then the bottom one and the top one does not have that many. And there are some differences between if we take into account wire capacitance and if we do not include the capacitance into the calculation. And also at the bottom, you see how important it is to include the area and position of TSVs on looking at the net distribution, as without taking those, we can make quite a big mistake. So it's important to do that. So summarizing that, it's we can say that TSVs are playing quite important role in evaluating the performance, and needs to be treated seriously when doing the physical design. Something which I did not talk yet about is the temperature distribution, and it's actually can quite change the distribution of wires if we use the proper parameters, temperature dependent for wires, and then for TSVs. And this is not only important because of the temperature, but also because of the density of wires and the spacing between the wires, which could be different on different layers, and this could again influence very much the capacitances. So here are just some pictures showing that there will be hotspots on those layers if improperly designed. With proper design and temperature-aware optimization, those temperature could be made a little bit more uniform. As you can see, the temperature could be quite different. Those numbers are in Celsius degrees, which you can see the 42, 75, 108, and of course the hottest layers are the ones which are far from the heat sinks. So of course there is a need for thermal modeling, need for fast evaluation, as most of the floor planning or algorithms are done based on using non-deterministic approaches. Then it's very time consuming if you would like to do each time the good thermal modeling. Therefore, the good fast thermal evaluations are very important. And so aside that, in order to help with the temperature distribution to be as uniform vertically and horizontally, they're using the different kind of dummy TSVs, and those would be carbon nanotube TSVs, which actually can distribute heat very well, temperature. There will be thermal wires, liquid cooling, different kind of materials which are put in between the stacked chip layers, which will help in horizontal distribution of heat, and of course heat sink materials. So with TSV started as the application mostly for image sensor, MEMS, and memory. We can actually see that now it's driven by the edge computing and by extensive use of very powerful sensors, which process the big data and need a lot of computing power in order to be able to use the data that's collected. So I was telling you all those wonderful things about those 3D stacked chips, but so if so wonderful, why we are not using them commonly? So there are actually major hurdles which needs to be overcome, and the big are the design issues, as those dies which are in the stack have to be designed in some integration. It has to be designed. They cannot be designed separately, and there's a. In many cases, those different chips, stack chips, are fabricated in the different facilities, but there has to be the very close collaboration, starting from initial design to the final test, between all the partners which are working. So the manufacturing steps have to be very carefully coordinated, even they are processed in different manufacturers. So far, the memory sensor, they benefit more than actually their difficulties with the technology, but there's a steady increase in the technologies and designs, which will definitely increase the number of ambitious and groundbreaking 3D projects. So clearly, that's the technology for the future. So those major hurdles will be overcome. So let's look at monolithics, and so this is, like, you can say, more than TSVs. And so the monolithics are layers of transistor fabricated one on the top of the other. What you see here is the picture, when on the bottom tier you have PMOS, and then on the top tier you have NMOS, and there is a very limited connections between the two transistor line, and most of the connection is above that. So it allows for it was allowed by developing the new transistor type processes. The connections between two layers is very dense. Those MIVs are very small, so the number of those connections could be large. This is still developing technology, but it's actually looked very, very promising, and the number of devices could be 2, 3, and depending on the technology and the need, could be probably more. This is just to show the very simple process of fabricating those devices, the monolithics. We start with the bottom device, and then there is a second wafer, which is some kind of the sandwich of the silicon between two oxides, which is put on the top. Then the top layer is stripped, and the next device is fabricated. I could see that I don't have that much time, so I'm trying to speed up a little bit. So there are 3 basic types of those sequential integration. Monolithic, and it could be the transistor level, where we have one layer with one type of transistor, PMOS, for example, and the top layer would be with the NMOS. There are gate levels when the PMOS and NMOS transistor are on both layers, and the whole gates will be on one layer or the other. And there is a block level, and there is a block level, which is shown on the bottom, which are just the whole blocks are placed on the other layer. And depending on which of this integration method used, there will be the different physical approaches to that. What you see on the right side is actually how those, if we use the standard cell methodology for designing those chips, then how there is a, how they transform from being just 2D standard cells to, for example, the second one is the folding. So basically we folded that standard cell such that one transistor is on the top, the other one is at the bottom. Or the last one, which is specially designed for the monolithics, when, as you can see, the buff VDD and VSS ground and power are moved to the top for the easier access, and there are some other ways to also to make those standard cells more efficient. So here I just want to probably show that the huge difference in the sizes between TSVs, which you see this big circle here, 5 micrometers. You know, even TSVs are shrinking a little bit, but still the sizes are large. And then the 50 nanometers diameter for inter-tier via or monolithic inter-tier via, which are used for the connections. So there's a huge difference. So the number of connections for monolithics between the different transistor layer could be much larger. Okay. And then looking to the future, to the emerging devices, those are new developments which shows recent technology and advancement. And this is for at the IEDM 2018 show that for the sequential integration, actually stacking of FinFET devices, one on the top of the other, looking at the comparison between stacked 3D and monolithic from the point of view of physical design, the big issue is how we are going to represent the modules and TSVs Island or TSVs during the optimization algorithm. So for stacked 3D, we can partition our system into different layers and then use just the regular 2D floor planning and 2D representation, or we can use some pseudo 3D representation where there will be simultaneously designing and moving modules between the different layers in order to optimize the system. For true monolithic 3Ds, it's a little bit different, because with true monolithics, for example, some of the modules could be truly three-dimensional, so could stack for the number of transistor layers, where other modules could just occupy one transistor layer. So really, in order to design them, there's new representations which are needed and new methods for do 3D floor planning. And again, many non-deterministic algorithms are used. We've been also implementing recently deep learning algorithms, and they're actually quite promising. So I just want to touch that subject a little bit, that there are some possible opportunities for hardware security, and this is with the split manufacturing. So something which we said there was a problem because the different manufacturers are, when they are manufacturing different chips, they have to talk to each other. But this could be actually used for help with this protecting intellectual property, as there's a separation between different part of the system. Another opportunity is with the camouflaging. So it actually was published that the people who were looking at the standard cells with the cells without camouflaging, which are the ones A, B in the top row, and then using the camouflage dummy vias, which is C and D picture. So this is quite well-known method of protecting IPs. Those are actually, we're looking at NAND and NOR gate. But then when they design those camouflage standard cells for the same gates for three-dimensional monolithics technology, it turned out, and you see them in the bottom row. You see the bottom and the top and the bottom layers of those gates. It actually turns out that they were able to reduce the area and power overhead due to camouflaging, and there was just a slight degradation in timing characteristic, but claim not much. So here's another opportunity of what we can see for hardware security in 3D. And there is something, and this is just the picture showing those chips. Forgotten about it. 2D. First is the 2D without camouflaging. Then there is a 2D chip with camouflage added, which increase the area. And then the third one is looking at the monolithics bottom and top tier with the camouflage. And here is another interesting development, which is what it's called smart TSV. So smart through silicon via. So the via is actually used, is designed as the transistor, FET. And as you can see at the bottom on the left, there is a source is at the bottom, and then you've got the drain and the gate on the top. And that connection, that via, is used as a transistor, which could be turned on and off. And you can actually see the single version of that and double and triple design version just about that. So interesting concept, which could actually help with also with the security. So the chip could be activated, deactivated, could be actually, interesting idea with that technology. So devices. As when you're going to, because eventually we're looking at the 3D integration. So those are devices, and the packaging methods. And we talked about the different packaging. Now let's look at the devices. So this is just the very typical path for the devices going to from strained silicon, silicon germanium, and metal gates, and so on, FinFETs, graphene FETs. And as it's being discussed, we were able for quite a long time to make some innovation by scaling or some small changes. However, it's predicted that we will just have to do the complete innovation going forward, as the small changes will probably will not be enough. So new devices, new ideas, and this is just some assembly of different devices we're using right now: silicon, non-silicon, with CNFETs, spintronics, and different 3.4 and 2.6. 3.5 and 2.6 devices. And the most recent innovation are those gate-all-around, or actually transistor made with ribbon. Here is the picture of device ribbon FET, which is Intel version of gate-all-around. And in addition to that innovation in the device, the Intel is proposing also something which they call power via, and this is the idea of moving interconnects below the devices, because so far all the interconnects were always fabricated above the devices. So they're proposing to have the power delivery network at the bottom. And they're claiming that they're will be getting quite a big advances. And Intel is actually predicting that they will be able to have introduced 20 angstrom devices in 2024. It would be really interesting to see that. Recently announced from IBM 2 nanometer device, and this is like the tiny nanosheet devices, and it's actually smaller than the width of the single strand of human DNA, and that's what IBM is announcing they will be able to fabricate. On the left, actually, I've shown some of the, you might say right now that this is old picture of the regular FinFET, and then transistor with the nanowires and the transistor with nanosheets. And those which are announced by IBM, those are the ones with the nanosheets. They're claiming that there will be quadrupling cell phone battery life, and the carbon footprint will be slashed of the data center, and the laptops will be much faster, and so on. And actually, they will be able to use it in autonomous vehicles. Here is some view of the IMEC transistor roadmap and new exotic devices with the different exotic carbon nanotube FETs and spin wave magnetic cores and so on. I hopefully have a little bit still time. I wanted to look at some of the application of those heterogeneous 3D integration, and one of those is application for RF and millimeter waves. That area was kind of left behind when the digital took over, and where digital systems were scaled and actually improved in performance. But it was really not happening for those RF and millimeter wave devices. And now with the heterogeneous integration, there's a lot of research going into bringing all those technology together in order to be able to make progress in that area. And what you see here is the first one is the Monolithic device, which is actually on the same wafer, silicon wafer. You have CMOS devices, and you have the HMT device, which is built using some etching process, and then growing the gallium nitride and indium phosphide transistors. So really interesting technology. Another one is the using monolithics and chiplet integration method, separate processes on one wafer, and they are using what they call IPD, which is integrated passive devices. There's a type of integrated passive devices, and then they are using low temperature co-fired ceramics in order to fabricate at the bottom those layers for wiring, and then integrated passive devices, and then putting on the top the chiplet with the IPs, different IPs. So some other new things about this area for RF and millimeter waves. You have another approach to fabricating, to using two different processes on the same wafer, and this is based on the wafer bounding integration. And you have the gallium nitride, which are at the let me see, which are at the bottom of the picture on the right. So gallium nitride transistor, and then on the top you have the silicon-based CMOS circuits, and they're done based on using wafer bounding. And it's actually, there's a lot of benefits which comes with that process. And of course, there are still problems which needs to be solved. And some of those problems are RF inductors, the crosstalk, and electrostatic discharge protection. And there are proposed solutions which are in the research stage based on my information. But there are vertical magnetic core inductors, which looks like to be the solution. And for crosstalk, they build the metal-filled walls, which separate devices to reduce the crosstalk. And they have some interesting solution for electrostatic discharge protection, and this is based on graphene NEMs, which are used in that design. Some more of those. So basically, there are programs which focuses on those on bringing those different technologies together for that specific application. And they're mixing those stacked chiplets, and then high electron mobility transistors and HBTs, and this is done on the CMOS. Another program where you have embedded chips in the wafer material, putting the different type of the technology onto the same substrate. And of course, what we mentioned already, wafer bounding, heterogeneous 3D DI. So very interesting combination of different technology. Here's another, just the one slide about this project, which I found, which is, this is the infrastructure which is built to, and which is founded by the European, this is companies, and this is the Human Brain Project. And the reason I'm mentioning it here together, because this is really the project which will be based on bringing all those different technologies together in order to create those chips which can be used in the neuroscience, brain medicine, and different kind of brain-inspired technology. So you can see, like here, it's shown in 3 layers that, at the bottom, there are different technology components which are developed by different companies, and the companies which are participating, they are changing, so I'm not sure that this is actually the latest one, but there are different companies, many of them, which are in the project. And then the second row are the different heterogeneous integration technologies which are used, mix and match. And on the top, you see the different kind of application. What I see and what I think about this heterogeneous 3D integration, this is basically something which, you know, it started with just relatively simple 3D integration with some image sensor memories and so on, and they had some you know, that they had some issues, but you know, with the time passing, there is a new development and new technologies coming, and I think that Monolithics 3D were the game changer. Even the work on those 3-dimensional transistors been going on for many years. But bringing all this together, and with the really the sensor being the driver for those applications, basically what we can say that, you know, integrate whatever you can, integrate sensor, IC, passive components, everything together. And this becomes very important for wireless, for 5G, for system sensors, for different kind of IoTs, and just makes it all what you can. And as long as you can design and test it and it will work, then this is great. This is really great opportunity for people who can imagine how those different technologies could be brought together and used. So this is what I think. Just play on what you can, as long as the music is good, right? So mixing whatever makes sense for new revolutionary application and is technologically possible at the reasonable cost. So I think that skilled engineers can do whatever is, do the wonders. And I want to thank you for listening to that talk. And I actually wanted to say thank you to my son, Marcin Jeske, who is always assisting me in polishing polishing my presentation, and he did this also with this one. So thank you very much, and I'll be happy to answer any questions.
Thank you, Malgorzata. That was very interesting, and I believe there are some questions I could see already in the comments section. I can also see that you mentioned many subjects that would require another 2 hours probably to be all the questions to be answered. But let me read those that I can see here. So first question for a person who calls himself Daniel. I don't see the affiliation, but the question is, when will 3D cooling channels be designed in to quickly remove 3D core heat to external cold plates?
Well, I know that there are experiments with actually doing microfluidics for cooling the chips. Been already, the people were working on that. When it will be available for the use and for the external cold plates, well, I don't know. It's it's very difficult to predict. What I'm thinking is that actually this kind of technology is speeding up very much, as I can see. So something which was seen almost impossible a few years ago, now we just see that there are some people who know how to do that, or at least doing the prototyping with that.
I think they do also a kind of thermal vias in some cases. So adding like pillars that just are used to conduct heat. Okay.
Yeah, that's true. I mentioned the vias with the carbon nanotubes, or just the vias to remove the heat. But that's I think that's a little bit different what the question is. Sorry.
Yeah, I think so. Yeah. Next question, I think, is from I think the person whose name I had somewhere, Ioannis Savidis from Drexel University, but unfortunately he left the questions but had to leave the meeting. But I will read the questions anyway because they are quite interesting. So so first of all, he thanks you for the talk and ask, can you explain the benefit of monolithic 3D for heterogeneous integration? Because it seems the benefit of monolithic is for homogeneous systems and not heterogeneous.
Well, I think that for me, when I say heterogeneous, it would be bringing all those technologies together. So if this might not be yet possible on the one wafer, but it could be brought together into the whole system and integrated, for example, as a separate chiplets. So this is, and thinking about, definitely I've seen the research where there's carbon nanotube transistors on the top of CMOS. So if this would be possible to do 3.5, I don't know. It's probably more difficult than with nanotubes. But with nanotubes, it will not be really that much. Probably not that difficult, because the process for fabricating nanotube transistors, carbon nanotube transistor, is very similar to CMOS.
Okay. Next question. I think is also from Ioannis. Did you compare your own electrical and thermal models with models that have been developed over the past 15 years? Whatever it means.
I'm not sure about exactly what the question is. We're working on developing the fast way of evaluating, and we're comparing with the previously developed very accurate model. So, for example, the Eurothermal model developed. There's a program developed by Stan Mircea, which is Hotspot, right? Which actually goes through the simulation and gives the. There are the algorithms or evaluation done by Jason Kong, which is not going through all the simulation, but has some simplified ways of doing that. So when we work on that, we are comparing with them. However, our goal sometimes is different than the goal of getting the complete distribution of the temperature over the whole layers, because when we make a decision in the floor planning, which is the good solution or not, I need to have the answer: is this solution is better or the other one? So the goals of doing that evaluation sometimes is different.
Okay, thank you. And I think still from the same lab, we have one last comment or question. Can you comment on the relative cost process-based of integrating 3.5 using the hybrid monolithic process, as you showed, as compared with TSV-based integration or heterogeneous processes?
On the cost. let me see. I'm trying to look at the question. Here it was. Okay. Magic, which question that was? I'm trying to read it. Can you come? Oh, here.
I think
I see.
it comes on the screen, I think.
Cost. Yeah, I see that. On relative cost process base of integrating 3 using the hybrid monolithic process you showed as compared to a TSV. You know, it's actually really, you know, it's really difficult because, you know, what do you include in the cost? Are you looking at the just cost of fabrication, or you're looking at the cost overall of designing, testing, and everything? Let me just say that I think that that all the parameters, you know, all the factors needs to be taken into account when you try to decide which processes you will be using for whatever application you want to do. You know, I'm not sure that I'm able to do the comparison.
I think if I can comment on this as well, it depends on particular process you are using for a particular design. I think it's very, you cannot give general comments on this. It's very difficult. That's my feeling. Okay, I think this that was the last question. I can see that Ricardo wrote the last call for questions, but none is appearing. So I think at this point, I will again thank the speaker. Malgorzata, thank you for this excellent talk and bright ideas and new ideas. I hope it will encourage people to work on this subject. I think it's a fascinating subject. And I would like again to repeat that it's a fantastic idea that came from Ricardo Reis and organizing this series of talks. And thanking for this excellent talk. We are looking forward to next presentations, as Ricardo mentioned at the beginning. So Ricardo, you can take the...
There is a new question by Yuanqing Sheng from Beihang University, China.
Okay, we can still do it. You allow that, Ricardo?
Sure.
Over time, we have it on the screen, but I will read it. Yuanqing Sheng from Beihang University. Thanks for the great talk. Do you think we need to consider the stress of MIV in M3D, like TSV in TSV 3D, except for size? What other main differences?
I think the size is really the big issue because they are so small that, and also they do not, when you see that the connections are really going between the transistor layers, so they do not go through all the silicon. They do not influence the interconnects that much. So I think that unless this is for some very specific research when you are doing the physical design, I do not see the need for considering that. And with, you know, it's always possible to do the simulation and see how much it changes what's surrounding. But based on my feeling, it is not, at this point, important.
Okay. I hope this is the last one. I believe if you have some more questions or comments, you can always contact the speaker via email, sending your questions, and I'm sure Malgorzata will be happy to give you answers.
Of course, yeah, especially that from questions, a lot of times coming great ideas, you know. So really the questions are the inspiration for you know, thinking outside of your own box. So please, if you have questions, I'll be happy to think about it and write your response.
Okay. Ricardo, thank you, Malgorzata, for all the comments.
Thank you.
Thank you, Maciek, for sharing this session. So it was great to see you again, and
my pleasure.
for me, you was one of the best president of IEEE Sequencing System Society ever.
Thank you.
And
Don't
also,
exaggerate.
thank you very much, Malgorzata, for the very nice talk in a very interesting subject. Thank you also to all participants to this session today, and also would like to thank to all you that include questions here to Malgorzata. By the way, the last question by Professor Yuanqing Sheng from Beihai University, China. There is also a very nice talk that he has done in this series of CASS talk that the recorded version is available in this YouTube channel also. So I recommend you to search for his talk and to attend, and thank you also to all other that include questions here, and to all other attendees to this session today. So today we had attendees that included their affiliation location, the YouTube channel. Someone normally that attended the talk didn't reply to our request to include their name in the chat channel, but consider the ones that have included. We had today attendees from Canada, USA, Spain, France, Argentina, China, and for sure Brazil. So it's thank you very much.
And from Poland and Germany on the way to Poland.
Yes, also. So thank you again, all the attendees, and thank you again, Maciek and Malgorzata, for this very nice session today. And see you next week in the FCBCCI sessions. Bye-bye.
Thank you.
Thank you very much.